5G is taking over more and more. Actually, in this period of time, we expect that in 5 to 6 years from now, the 5G will be the dominant mobile access technology, with around 4.4 billion subscribers. In this period something about the data in 5 to 6 years from now, 5G networks, we expect to have around 62% of the traffic, mobile world traffic, in 2027. And smartphones and video are really the driving for this quite extensive traffic. And already now, video is around 69 or 70%, and we expect that to increase going forward. And I think it's quite amazing what we see on average now. On average, monthly usage per smartphone is around 11 gigabyte per month. And our estimation is that the end of 2027, it will be 41 gigabyte. Also, the global monthly network will increase quite dramatically from the end of this year until the end of 2027, with the 5G taking a major part of the traffic here. Also, some information about the differences in different regions. We see now that there is quite a difference. Looking on sub-Saharan Africa, they will increase very much, but from a very low level. On the other hand, actually, India is quite interesting in its growth and expecting to reach top of the usage by year 2027. But of course, this requires actually a spectrum also. And that is one of the key ingredients in this. There is a situation here with the migration from 4G to 5G, with the lead being at the moment in North America and in Northeast Asia. And also to some extent almost similar is actually the Western Europe. According to our estimation, the situation in Southeast Asia and in India is lower than that. So I really hope that we can see a difference or a catch up in this region to the estimations that we see in North America and in Northeast Asia and Western Europe. But it looks like our estimations here, India will be a fast-growing country in this aspect. Looking on what we see from, this is from a GSA report, quite recent. Both this information is from November and December reports they produced, and we have now around about 170 operators in 68 countries that has launched 5G mobile service in some way. And the devices are catching up very, very fast. As you can see here on the device map, it is the C-band that is taking the lead here. But also other bands, like the N1 being the core band, the 2 gigahertz. We have the 4.5 gigahertz. We have 850. We have the 28 being the 700 megahertz, and then also we start to see the growth of the millimeter wave, and that really is the key component to provide the full capabilities of 5G in combination with the low and mid bands. The millimeter wave is a key, and also it's over 1,000 announced 5G devices now in total, and quite a number of different form factors related to fixed wireless access and other types. So it is really growing extremely fast at the moment, the take-up and the device take-up creation by a number of vendors related to this. So if we then look a little bit on history when it comes to what ITU has done and what we see going forward. I mean, this started, it was before my time, I must admit. It started around the mid-80s, and then the vision here for IMT 2000, that work started at the end of the 80s. And the first version, I think, was published around 1992, and was actually enhanced until 1997. Two recommendations here, and this was as some of you might remember, it was called FPLMTS, Future Public Land Mobile Telecommunication System. Too complicated, so it was modified to IMT 2000 in the 90s. And these two recommendations, they provide the sort of concept and thinking about a global, worldwide communication system, IMT. And it started with quite sort of low-key in this view nowadays, 144 kilobit per second on vehicular system and 2 megabit per second in the indoor and slow mobility environments. Then we came with the IMT Advanced, and quite a big step was made, up to 100 megabit per second and 1 gigabit even in certain environments. And this was done with the Venn diagram, which I think was really a key insight into what the ITU wanted to achieve with a new mobile system, the 4G. Then we came with 5G, the IMT 2020 and recommendation 2083, MDOT 2083. That was developed during 2012 to 2015. And here I think we have seen quite a big change from data to actually various user and technology trends encompassing the entire society with different usage scenarios. And we have the spider web diagram, which I think was really beautiful. It was a new thinking and it really created a lot of attention. And then the peak data rates and user experience quite dramatically increased. I think we need something similar to this, something picturing the future and what do we want to see. This was a really good development and production from ITU in my view. So we need something for the IMT 2030 so-called vision that is being developed now until 2023. And we have received quite a number of different positions and views from industries, research institutes, and forums in viewing the possibilities and the vision for 2030 and beyond. So then we are at this point at the moment. We have the 3G, 4G, 5G done. We have the family members under IMT, and these are very important because most countries nowadays are actually licensing the mobile and to IMT, mobile communications to IMT, and 5G plays a very important role there. So now we are looking into 6G, and considering that we have for 5G, we have at the moment the 3GPP, and we also have in India the TSDSI technology, 5GI, based very much on the 3GPP solutions, and recently also a DECT actually, and we might expect that there might be some additional technology added here. But then taking this into consideration, what do we do for 6G? And here I want to point out some changes that we have seen in the development. It's in principle we see that both when it comes to the vision, as you see here, it's starting 1992. And every 10 years, sort of, roughly, we have a new vision. And that is what we are working on at the moment. And then the same is for the requirements. So we need to have something related to the requirements, in my view, in 2027, 2026 timeframe. And as you can see, it gets more and more concise also. So having it clearly developed, I think is an advantage for the industry to work and develop its specifications in a concise manner based on requirements that are very clear. The submissions is the same. You can see the time frame is roughly 10 years. So we expect we need to have something by maybe not to 2027, but 2028 or so. And also when you look on the evaluation, it's a similar. But here one can note perhaps that the amount of instructions is growing, and we need to perhaps look on this, what we need to do for 6G. And then the specifications, every 10 years roughly, and we have the plan for 2030 coming up for the IMT 2030 so-called. If you look, we look on what is happening in globally. It's a lot of initiatives, regional and national initiatives regarding 6G, but also IMT 2030 in a sense. And many of these studies will actually conclude 2023. But some will also plan to continue. So this is happening now, and it's important that we see the ITU as a focal point in this and contribute to that progress. And here we can, I try to sort of grab what we need to do going forward. We have a lot of experience now with the previous generations. We have the definition phase. We know what it means, roughly 2-3 years. We have the requirement phase, maybe 2-3 years as well. We have the proposals that we need to come in from the external organization to provide the content, the real specifications, the real ideas for the development of the detailed specifications that we want to produce. So here, external organizations plays a very important role. But we need to start. We need to start in order to have all these deliverables developed. I mean, the process here that we had, which was very successful, had something like 12 deliverables developed. And this was, as chairman of the ad hoc work planning in Working Party 5D, I suggested this schedule for the ongoing work towards 2030, roughly 1 year ago. And it's very much based on the previous experience we have had in Working Party 5D. First, we have the starting point, describing the vision. We have the requirements developed. We have the external organizations working, and then we see what ITU wants to do with that information. And the current situation is that we have agreed to have the technology trends, new technology trends developed. We have the agreement to do the vision and also a feasibility report on spectrum above 100 gigahertz, and to finalize the standards in year 2030, IMT standard. And what we are discussing at the moment is the timings and deliverables for the period between 2024 and 2030. And I think this is really important that we can conclude on this during next year, so that we have a solid schedule to present together with these other deliverables that we want to finalize before year 2023 and the WRC 23, so that we could, if we want to, promote an agenda item for WRC 27. And this is what I have proposed, two options here, as you can see, as ad hoc plan chair in Working Party 5D. And there are other options existing, so this is just something for discussion. But we have agreed on the schedule toward 2023, and we have agreed to finalize it in 2030. So something on the future technology trends, the report that we are developing. It's describing, it's very interesting contributions, and these drives the specifications work in different organizations, and also it is a basis for the discussion related to the vision, which might be the key document. We have the current driving factors in the design of the INT technology, very many different aspects here, data rates, latency, jitter, sensing, etc. And also technologies to enhance the radio interface. We are back to modulation, discussing coding, but new ideas on extreme Mimo and also full duplex has been discussed for a long time. But what will we see in 6G? And enhancing the radio network. We have technologies for artificial intelligence, very hot topic now. What will this mean to the network, to the new interface, ethics, etc.? And also technologies to enhance in various ways, service, again, coverage is really a key, and here India has played an important role in the discussion in ITU, and this will also be, in my view at least, be important for 6G. Coverage is still the key, and will be so going forward. And then some comments on the recommendation of the new ITU vision that I mentioned a bit earlier. This is the key document going towards the WRC 23 and beyond. So far 5G has sent out an invitation in a circular letter to external organizations, around 50 of them actually, and to provide views to the process internally in working party 5D. And we have suggested to provide as early as possible, but no later than June meeting number 41 next year. And we hope that we'll get some contribution to the upcoming meeting in February, but then we hope that we will see the final inputs in June next year. And then we will also have actually a workshop planning for June next year, and that will be announced in some sort of information, either a liaison or circular letter out from the February meeting. Currently, we see in the vision document we are developing the trends of IMT, and here we have, it's very comparable to what was done in the previous 5G cycle, user and application trends, technology studies on and technical feasibility, and now for IMT in bands about 100 gigahertz. We are extending that. Previously it was about 6 gigahertz. Now we are going beyond 100 gigahertz. And also spectrum implications. We have evolution and role of IoT is very key actually. Usage scenarios, what do we expect, and capabilities beyond for IoT 2030 and beyond. So to summarize here, when we are talking about going from 5G to 6G or IoT 2020 to IoT 2030, the recommendation we have now on IoT 2020 specifications, it's M.2150. It was approved in February, early February this year, and it is a very successful completion of 8 years of work and around 12 deliverables that we did. So it's a very solid and amount of work that we accomplished, and I think it was very good, since it really commits all the engagement organizations in this, and I really hope that we could do the same for INT 2030. And the vision recommendation, that was all the basis for this, and you see these figures. I don't know how many times these has been shown on different conferences and seminars. So they are really important. And the evolution is ongoing now. It started both in ITU and 3DPP for various enhancements of 5G, but also on 4G actually. Now we have the start of the new vision, and it's complete, scheduled to be completed at year 2023, and that we have the new IMT technology family member, IMT 2030, to be finalized by year 2030. So that's an agreement. and commitment that we have. And I think we need something similar of the successful document that we did for 5G. Now we need something for 6G. And I really hope that India can contribute in providing not only views for India, but actually for the global community, and that India can contribute in a harmonious way to this future technology trends and to the vision. Thank you very much.
Thank you, Mr. Hakan. There are certain questions in the chat box, and also we got it through other channels. If you like, I can present those questions to you, and you may like to answer them.
Please.
Yeah, I'll just do that. So, can you unshare your screen so that I project the questions?
Yeah. Oh, I need to figure out how to do that. I can't find my.
From where you shared the same, if you just click that.
Yeah. Sorry, I can't. I need to
go to the window where.
I need to escape. Okay, here I am. Here we are.
Okay. Can you see these questions on your screen, Mr. Hakan?
I have problems too.
So I'll read for you. The one question is that it is seen that Open RAN labs and testing facilities are set up at many places around the world. If any academic or such institution want to set up such facility, whether ITU can support?
I have difficult to answer that, being I'm not an ITU official, so I would like to refrain to comment on that question.
Okay, fine. Let me take the next question. So, how do you see the role of 5G and going forward 6G in terms of reducing carbon emissions?
Oh yes, that is a key component actually, and it has been discussed in the future technology trends related to sustainability. I think it's on that slide actually, and it will also be in part of the vision. I'm very sure it will be a key component going forward. Absolutely, it's a good point actually to bring up and take forward, and also the energy efficiency, etc., and things like that. That is important to developing countries. So please, if India can contribute to this, I think it's a very good way to provide the information and suggestions to the activities.
Yeah, thank you. I'll read one more question. So this is with large swath of spectrum being put up into use as we go into 5G and to 6G, will that be a concern with respect to radiations emitted?
That is a little bit also beyond my perhaps knowledge, but I mean the spectrum is a key here, and how to it depends of course on the ranges we are discussing, but maybe the assumption is that we need some smooth migration here from 5G, 4G, 5G going to 6G, and then all the frequency bands that we are using today needs eventually to migrate, and we need to have some good technology in order to do that in a very good way. So then I don't assume that there will be a big difference. But of course, if we go up to extremely large bandwidths, this might be an issue. Yes.
Yeah. So there's one more question. Are there any standards evolving for street furniture designs, like that of street lights, in order to accommodate base station in them?
That I heard, I think, when I started working on 3G, actually. And that was some vision also then. And maybe we are getting closer to that vision now with the 5G, actually. Getting close to it already. But maybe the 6G will be even closer.
Yeah.
I don't know.
I'm reading one question from the chat. What may be the focus area of development in 6G? So what can be the focus area of the use cases while developing 6G? That's the question.
Yes, I think now yes, okay, good. So here we see, if I then try to recall my research colleagues in the company, I think it's very much of resilience. We need to make sure that the future systems are resilient. They are very secure, but also I think that we now see that we are going. The 5G is quite business oriented, right? And perhaps we have seen this development in 4G, where we went to more personal and integrated concerns and opportunities. 5G is very business oriented, with new enterprises coming in and so on. Perhaps the 6G will be back a bit to also, of course, encompassing enterprises, but maybe even more personal, with sensors, with very much everything connected, including clothes or whatever, in a much more integrated way than with 5G. So perhaps 6G will be more encompassing, even further than what we see in the plans now.
Thank you.
So, sensing, I think, is one key among others. Yes.
Thank you. Mr. DG Deepa, Mr. TR Dua has raised
Sorry, hand. You are muted.
Yeah, thank you. Thank you for pointing out that. DG Deepa, Mr. TR Dua has raised hand. I have allowed your mic. So if you can open your mic and ask your question, Mr. Dua. Mr. TR Dua, you can open your mic and ask your question. So in the meantime, if you like to ask any questions, Sunil sir.
Good evening, Mr. Hakan. Actually, I just want to know, when you talk of convergence, IoT technologies mostly are on non-3GPP technologies right now. So going maybe around 10% of the IoT devices are on 3GPP, and remaining are on other technologies. So do you foresee some convergence happening there also in when 6G happens? So what is your, do you have any views on that?
No, I don't see the convergence. I think there will be a place for both for several technologies, actually, when it comes to IoT usage, and it's very clear that we see these the wide area cellular IoT growth, and we also see the massive IoT growth at the same time, and I think it's room for all various technologies here. But of course, it will. It is a difference between the different technologies when it comes to quality of service and what you need for them. Some needs really high bandwidth and low latency and resilience and security, etc. And then the 5G 3GPP technologies are outstanding, but others don't need that, and then new technologies will develop, and I think it's good for competition to have actually different solutions. So it's a challenge for all the technology proposals here, and I see it as an advantage actually to the market.
Okay, thanks. Ashok, questions from the chat?
Yeah, so there is no major questions, sir. All questions, sir has already covered. Maybe if you like to ask a few more questions, sir.
Yeah, actually, just one curiosity I have, like when you think of a lot of base stations coming in 5G and 6G on the streets, etc., and there are many operators, like in India, we have about 3 or 4 operators. So do you think that, this Open RAN thing coming up, do you think that this active sharing will be something like a mandatory in some countries, so that only one tower, only one equipment, only software, multiple will that be a trend going forward?
That's difficult to answer. Maybe I don't think it will be a trend actually, but it depends very much on the economy, etc., and the developments. But as I said earlier, I think the competition is good, and to combine too much and to limit the opportunities for business developments with the different operators is not that beneficial in the long term, but maybe short term to get the business going, it could be an advantage. But long term, no, I don't think so. That's my personal view. Yeah.
Thanks a lot.
So there is one question which seems to be relevant. As artificial intelligence being integrated into communication network fabric, how ITU plan to ensure lawful interception aspect is taken care of?
That is not my area, actually. I cannot answer that question, and I'm not sure if ITU should be the one to really develop such sort of requests or commands. To me, it doesn't sound to be the role of ITU, but it's not my area.
Yeah. So thank you very much, Mr. Hacken, for taking a very wonderful session and also taking up various relevant and some out-of-box questions, because from the almost 250 plus audience, questions can come anyway. So maybe I request Sunil sir to say thanks to Hacken, formal thanks to Hacken sir, and then we will take up the next technical session, sir.
Yeah, definitely, Ashok. So actually, we were really lucky to have you, sir, in our session because of your extensive experience in standardization activities. You are the right person to set the tone for our 6G session, because it's all about future and what lies ahead. And since you have been closely associated with the evolution of wireless technology in the past, you were the right person to, and you have dealt it very nicely, giving the entire path ahead and what is likely to happen in the years to come. And you, of course, are closely associated with Ericsson and have been in charge of all the IoT technologies. You were really benefited with your words of wisdom and knowledge. So thank you so much. for sparing your time from Vietnam. So all the while, and immediately accepting our invitation and coming forward and being part of our session here. So thanks a lot on behalf of HAPRIT and all the community in India, the technical community in India. I really thank you so much.
Thank you very much. It was very interesting to hear the questions, and I really hope I can contribute, since you know that India is in my heart, and I would appreciate to assist you in any way I can. Thank you very much.
Yeah, thank you very much, Mr. Hacken. And moving forward, the next session is on the network evolution to 5G advanced and 6G, and the session will be taken by Dr. Harry Holma. I already see Harry have joined the session. Sir, if you can open your mic and video.
Yes, I have my mic and video you're running. So
Yeah. Thank you very much. Now we can see you. Thanks a lot. So, without taking much time, I hand over the floor to you for your session, sir. So over to you. I'll just disconnect my one.
thank you.
Thank you.
Can you see my slide now on your screens?
Yes, we can see. Yes, it is full screen. We can see. Yeah.
Excellent. So indeed, thank you, Secretary, Head of Institute, and Sunil for the invitation here and for organizing this session. So happy to be part of this event today. Thank you also for Håkan for the nice presentation on the ITU side. And indeed, my name is Harri Holma. I'm part of Nokia Technology Office. I'm based in Helsinki, in Finland, and the topic today is I wanted to sort of look at where are we today in 5G in practical commercial deployment, and then focus on 5G advanced and 6G technologies. And the picture you can see here on the background is the new Nokia Arena. It is the sports arena that was opened just recently, I think last week, and it's a nice test environment also for the 5G technologies, because it can house, I think, like 15,000 people all together for any kind of like sports events like ice hockey. And in terms of local conditions here, so I'm right now in our office here in Finland, and the temperature outdoors is minus 15 degrees. So of course, you know that all the RF engineers would like it, because RF noise figure is getting better in the low temperatures. So we have now excellent coverage here in Finland today. So, but let me go through some of the material, and if you have any questions or comments, I guess you can use the chat window, and then I can try to respond those at the end of the session. And I wanted to start here by showing where are we in practice in 5G technology today in end user performance. And I'm summarizing here a few example drive testing results, kind of indicating the practical benefit that 5G is able to deliver commercially today. And I'm taking here a few example cities. So the local case here in Helsinki, another case is Busan. Busan is in South Korea, and the numbers here are indicating average throughput in drive testing. In typical 4G LTE networks, the average data rate has been around 100 megabits per second, and that was also the case in the recent measurements in Helsinki. If you look at the same conditions, same drive testing, 5G device and subscription is able to provide on average roughly 500 megabits per second, which is pretty impressive. I mean, you can drive around here in the city, and on average you will get half a gigabits per second data rate, so roughly 5 times more compared to LTE 4G. If you go to Korea, like Busan, the data rate is even more impressive. The main reason is that the Korean networks are extremely dense. South Korea was the first country globally opening the commercial 5G network in April 2019. So the networks are extremely developed. The average data rate in Korea even around 900 megabits per second. If you look at globally today, the average data rate benefit of 5G compared to 4G is about 6 times. So clearly showing that the underlying technology for the mobile broadband has been able to deliver the expected performance. And what are the key technologies needed here is mainly a new spectrum. So we need to have new TDD midband spectrum, which is typically 3.5 or 2.5 gigahertz band. Secondly, we need to have a new RF, new antenna, preferably massive Mimo beamforming antenna, and 5G technology. And when you combine those three together, new spectrum, new antenna, 5G, indeed you can get pretty nice practical performance. Let's look at some of the other technical details here. What are key ingredients to provide a great 5G network? And of course, spectrum is always the important part of any wireless solution. The midband spectrum is the mainstream solution today because that spectrum can provide quite high data rate, peak data rate, 1 to 2 gigabits per second. And also the midband spectrum can provide quite nice coverage, especially in the urban areas. And mobile operators are able to reuse the existing 4G LTE base station sites for the 5G deployment and get roughly the same coverage as 4G LTE. We also need to have some low frequency bands, so low band FDD. That has been also widely deployed globally. The low spectrum can provide extreme wide area coverage. It can provide indoor penetration, but then of course the data rate is then lower. But in practice, we need to combine these spectrum resources together. Low band spectrum needed for coverage, for uplink, midband spectrum needed for high data rate. High capacity. And the third important spectrum block in 5G is so-called millimeter wave. And the name is coming from the fact that the wavelength is just a few millimeters. The spectrum globally is around 24 to 28 gigahertz or 39 gigahertz. And that solution can provide even higher data rate, up to 4 and 5 gigabits per second, which means that the millimeter wave is an ideal solution in the extreme hotspots, also providing connectivity solution for fixed wireless access or enterprise cases. So kind of the beauty here in 5G is that the very same technology can utilize multiple different spectrum blocks to provide the kind of ideal combination of coverage, data rate, and extreme capacity. Also, what other learning is that spectrum is important, but also the beamforming antenna, so-called massive Mimo antenna, is highly important for maximizing 5G radio performance. And we need to know that 5G technology is the first ever 3GPP radio that has been fully optimized for the beamforming. Beamforming was implemented in LTE, but it was not included in the very first LTE release. In 5G, beamforming has been included from day one. And that is one of the underlying explanations or technologies that is needed to deliver the great radio performance. And a lot of activities are happening on this area to make the beamforming performance better with the new algorithms, like different kind of beam refinement, feedback solution, sounding, reference signal, beamforming, and so on. The other area of improvement is AI/ML, so artificial intelligence, and machine learning are in practical use in the 5G networks today. And beamforming optimization is one of the application areas of AI. So clearly we don't need to wait for 5G advanced, we don't need to wait for 6G to get the benefit of AI solutions in practice. And AI can change, for example, beam sets, down tilting, beam widths, common channel beamforming as well. And the third area of improvement is then so-called multi-user Mimo, where the idea is to use beamforming for maximizing the capacity. The idea is that multiple devices can reuse the same resources in time and frequency domain if they are located in different beams. So the idea here is trying to identify the most optimal devices that can receive data at the same time in the different directions. And by doing that, the operator will be able to maximize the network capacity and efficiency. And then I picked here some example practical cases. So I'm lucky to have 5G coverage at home. And also I'm lucky to have fiber connection at home in Helsinki, so I did some simple personal benchmarking. With a fiber connection at home, I can get close to 1 gigabits per second, downlink data rate, uplink about 200 megabits per second, 5G at that 3 to 5 gigahertz band. I'm able to get also roughly 1 gigabits downlink data rate and uplink about 80 megabits per second. And now if you are comparing these solutions, so can we kind of replace fiber connectivity with 5G? The answer is that in the best case, yes, your downlink data rate is getting similar or even higher. But in uplink performance, typically fiber can provide a higher data rate than 5G. In 5G in TDD, we are using less time for uplink. And also the mobile output power limitation may have an impact on the uplink data rate. Also, we need to note here that in terms of latency, the mobile technology has some disadvantage compared to fiber. So the latency figure is slightly higher in 5G compared to fiber. Of course, in many practical cases, the data rate is high enough for the home connectivity, and in many cases, Wi-Fi 5 today will be the practical bottleneck. So if we don't have Wi-Fi 6 implemented in some of the devices or laptops, then the practical data rate anyway will be not more than about 500 to 600 megabits per second. Then also wanted to show here some results on the low band 5G. So remember that the low frequencies are great for coverage. It can be 600, 700, 900 megahertz frequencies. And I'm illustrating here some practical measurements in live network in Europe, where 5G has been deployed on dedicated 700 megahertz band. And what the customers are able to see here is not only the 5G data rate, but because of LTE dual connectivity, the data rate is the aggregated data rate of 5G 700 plus LTE 1800 and LTE 2100. And therefore the data rate is pretty impressive, like 350 or even 400 megabits per second I was able to get in my practical measurements. So the kind of story here is that even on the low bands, 5G data rates can be quite nice, partly because there is new, clean, empty spectrum utilized here for the new technology. And then secondly, because we are also aggregating the LTE performance here together in terms of dual connectivity. In Nokia, we also have done some testing of the 5G 700 megahertz technology in India with Bharti Airtel and achieving also pretty nice cell ranges of up to 40 kilometers. And that is the beauty of low frequency band. Your cell radius can be extremely large. Also wanted to note here that we have done some other testing in India for the 5G preparation, backhaul testing with the E-band microwave radio with the Vodafone Idea, roughly 10 gigabits per second. But the message here is that also the microwave radio is one solution for backhauling 5G base stations. No need to have fiber connectivity to every base station in practice. Then remember the third spectrum block for 5G is millimeter wave, and one of the benefits of the millimeter wave is extremely high data rate. Here we are illustrating an extreme case where 2 times 800 megahertz bandwidth has been utilized at 26 gigahertz band, and that was able to provide even more than 8 gigabits per second in commercial network. You can easily point out that nobody will need 8 gigabits personally. That is true, but 8 gigabits may be a nice solution in big events, like maybe sports stadiums where you have thousands of people together. Also, high data rate may be practical for truly replacing fiber connectivity at home, so fixed wireless access. And also, there's an interest to use millimeter wave for the enterprise networks for providing reliable connectivity in factories and campus areas. Most of the 5G networks today are using so-called non-standalone NSA architecture, where the idea is to use LTE core network, EPC, and use 5G radio for boosting the radio data rate and capacity. The next phase is already happening in the live networks, and that is the evolution to standalone SA network. And for that, we need to have new 5G core network. We also need to have the required technologies in the radio network. And there are a number of benefits and motivations to go for the standalone deployment. And that is what I'm listing on this slide. T-Mobile US has been, I think, the first customer globally using a standalone deployment in wide area 5G network. And that is already showing some practical benefits for the customers. The first benefit is that 5G coverage will be better in standalone architecture because there is no need for the device to send LTE connection. So all the power can be used for the 5G transmission. Secondly, we can also see from crowdsourced data that the latency is lower in SA case, which is also contributing to better customer experience. Slicing is one of the important 5G capabilities, and with the SA architecture, 5G core network, slicing can be implemented. Also, if you look at the radio performance, uplink data rate will be higher in SA case because mobiles can use 2x2 Mimo in uplink direction. In NSA case today, 2x2 Mimo is not feasible because devices need to send LTE and 5G transmission at the same time. In SA case, 2x2 Mimo is becoming feasible. And that is providing even more than 200 megabits per second in uplink when using 100 megahertz TDD spectrum. Also, simplicity and the long-term evolution are important part of standalone targets, and then also the device power consumption can be lower in SA case compared to NSA case. So clearly a lot of good reasons why operators globally are now gradually migrating to SA deployments. In order to make the network ready for the standalone deployment, then there are some important radio capabilities needed. And one of those is carrier aggregation. And carrier aggregation was not important in NSA case because the device was able to aggregate LTE spectrum and 5G spectrum together. But in SA case, that is not feasible anymore. And therefore, we need to allocate more spectrum for 5G. And secondly, we need to be able to aggregate those spectrum blocks together. And that is what carrier aggregation is about. And here we are showing one example case where Nokia tested carrier aggregation with MediaTek chipsets. And this testing was done with 3 component carriers, totally providing 210 megahertz of aggregated spectrum and providing peak data rate more than 3 gigabits per second. And these capabilities are now going to be available soon in practice also commercially in the devices. And clearly important requirement to make the SA deployment successful in practice. Then one of the important targets in 5G technology is to provide reliable connectivity for the critical communication. Also, the target has been to provide low latency communication. Sometimes that is called with the abbreviation of URLLC. And there are, you could say, 2 basic options how to implement this critical communication. The first option is to use public network with slicing. So the idea is that the operator can allocate dynamically part of the spectrum and network resources for one particular customer or application. And by doing that, it will be feasible to guarantee the performance, data rate or latency. And there are some example use cases already happening today. One example is public safety. There are some countries where the public safety communication is moving from dedicated network on top of mobile networks, or 4G and 5G networks. And for those cases, there must be solutions where the government, like policeman communication, can always get guaranteed bandwidth even under heavy congestion, like some emergency cases. Another practical example today is remote control of machinery. So if you want to control, let's say, like farming machines, if you want to control some like forestry machines or any kind of other remote machinery, we need to have reliable connectivity, and therefore the slicing can be the solution on top of public network. The other option is then to use a dedicated local wireless network. And the motivation has been typically such that there are cases like some airports or factories where Wi-Fi performance is not good enough. Like typically Wi-Fi works fine indoors, but if you want to use Wi-Fi outdoors, like at airports or some big campus areas, like factory areas, Wi-Fi performance is not good enough. So we need to have better radio, LTE or 5G radio. But in many cases, those enterprise customers do not want to use public network. They want to keep the data in their own premises. They want to have full control of the network. And therefore, the solution will be to deploy private wireless network. It can be based on LTE technology, and future, of course, will be based on the 5G technology. And there are some examples happening today. Nokia has, I think, roughly 400 private network deployments globally. There are like harbors, there are mines, there are factories, so a number of different kind of customers that need to have reliable local connectivity. So that was pretty shortly where we are today in 5G in practice, delivering mobile broadband and delivering then reliable enterprise connectivity. But let's then move forward and look at what 5G Advanced will bring for us. Now 3GPP has defined release 15, which is commercial today. 3GPP has defined release 16. And that was completed already end of last year, providing some better support for the industrial IoT. Release 17 work is now ongoing. The completion is expected mid next year. And the next phase will be release 18, which is now called 5G Advanced. And we expect that release 18 will be completed in first quarter 2024. Which means that the commercial practical availability of those features are likely starting 2025. If we then look at what 5G Advanced will bring for us is a number of different areas. And we can categorize 5G Advanced in 4 different areas. It can provide new usage areas, where the idea is that the same 5G radio can be applied to a number of different use cases beyond just smartphones, laptops, and normal enterprise connectivity. There is low-cost IoT optimization. There is non-terrestrial networks, so using 5G for satellites. There is drone control optimization. There is uplink coverage improvements to provide even like a deep rural coverage with the 5G technology. And then cycling is referring to direct device-to-device or car-to-car connectivity, which can be used also for the traffic safety. The other area of improvement is new services. So a lot of optimization will be included to make extended reality XR work better, cloud gaming work better, mobility performance better, and also support the better edge computing applications. The third area is boosted 5G resilience, where the idea is that 5G network can provide accurate positioning, and 5G network can provide accurate timing reference. Of course, satellite can also be used, but there may be reasons to rely also on the mobile network. Maybe inter-premises satellites will not work, and therefore 5G network could be the source of exact timing and exact positioning. And for many of the enterprise use cases, it is quite important to know the accurate timing and positioning. And the fourth area here is boosted performance with artificial intelligence integration. So better support for data analytics, slicing enhancements, and some CU resiliency as well. And if we then look at what kind of practical benefits there are, you can see that 5G Advanced will bring a long list of improvements in terms of pure radio improvements, capacity, coverage, Mimo performance, and in terms of application performance as well. But let me take one example here. So one potential improvement area for 5G Advanced would be XR, so extended reality, augmented reality, virtual reality. And I'm listing here 6 different areas where 5G Advanced can potentially improve the performance of XR service. The plan is that 5G Advanced will improve the scheduling, matching with the XR transmissions. Mobility will be more smooth than what we have today. Uplink data rate will be better. There are better power saving solutions to minimize the XR or VR classes power consumption. There is also better application awareness integrated in the radio. And then also one potential solution is to have a 5G low power side link connection between the VR glasses and your smartphone. And we also need to note that there's a lot of other activity in the industry to make the XR performance better. You can note that Nokia is also actively working on the video coding solutions. So a lot of innovations has been done on that area, contributing to better XR experience as well. And by the way, Nokia has 4 Emmy awards on this coding area as well. So what could be potential one use case of 5G Advanced is the performance and capacity optimization for AR and VR. And if you believe what Mr. Zuckerberg is telling, then his future social media service will be called Meta. And one of the key underlying technologies in Meta are augmented reality and virtual reality. So potentially it could be that in order to have efficient solution for the future social media, we preferably need to have 5G advanced underlying connectivity technologies. Then I wanted to list also a few radio topics in terms of 5G advanced improvements. One is coverage enhancement with so-called frequency domain spectrum shaping. But the idea is that if we are not fully loaded in uplink, it will be feasible to have at least 1.5 dB improvement in the uplink coverage by using some extra bandwidth. But the idea is that if we can relax the mobile out-of-band emission requirements, then the mobile will be able to have lower backup requirements, and by doing that, it can boost the output power. So we are kind of wasting a small part of the bandwidth, but then the benefit is that there's a major boost in terms of uplink coverage. And that is true for the data transmission, that is true for the low band frequencies, that is true for the millimeter wave bands as well. Another example improvement area is then mobility. And there are a few different solutions in 5G evolution how to make the mobility better. Conditional handover is a concept where we first make the handover before breaking. So we first prepare the target cells before breaking the connection. And then the other solution is so-called dual active protocol stack DAPs, which can minimize the handover interruption time. So the idea is to improve the reliability in terms of mobility, and the idea is to minimize any kind of connection break that we have during the mobility. Also, one area of the evolution in 5G Advanced is low-cost Internet of Things connectivity, and that is called Reduced Capability RedCap. And you may remember that low-cost IoT solution has been specified also in LTE. One solution was called narrowband IoT. Now the problem in narrowband IoT has been that the capabilities are extremely limited, a few hundred kilobits per second, and also NB-IoT requires quite heavy R&D because it will redesign the control channels. The target in 5G RedCap is to, first of all, provide substantially lower device cost compared to normal 5G. but at the same time still be able to provide reasonably high data rates in the order of 10 to 100 megabits per second, which means that the RedCap solution is good enough even for providing high quality video connection. Also, the target is that we try to minimize any changes needed in the 5G control channels so that the deployment of RedCap IoT will be easy on top of 5G networks. And then at the end, let's look at some 6G technologies, what we expect 6G is going to be needed. And I'm here illustrating a few example applications and the evolution on top of radio technologies. So let's take video first as an example. 5G can deliver high quality video, 4K, 8K. The target is that 5G Advanced can provide even better quality video with XR, so fully immersive user experience. And then in 6G area, the target would be to provide holographic transmission, again boosting the experience between the people's communication. The second area is also digital physical confluence, which means that today 5G can provide object-driven digital twinning. 5G Advanced target would be to provide large-scale digital reconstruction, so not only some individual engine, but to have like full area or factory area reconstructed. And then 6G will take it even further, like broad-based digital twins with real-time synchronous updates. And the third area is localization and sensing. I mean, today 5G providing data communication and control. 5G Advanced will boost the capabilities with a precise location and precise timing services provided by the network. And then in 6G sensing will be one of the key capabilities. So the idea is that the RF technology is not only used for communication, but RF technology can also be used as your personal sixth sense, kind of helping the kind of personal life. And what we need to have then to make this all happen, we need to of course work on the new spectrum technologies. We need to work on the new air interface where AI has an important role. We need to look at the sensor technologies, security important, energy efficiency of course will be important, also automated and cognitive deployment will be important as well. And these are the topics we are already starting to work internally in Nokia and in international projects together with the universities and other vendors on the topics. And if you look at what the spectrum potentially could be in the future, remember in 5G we have the low band, mid band and millimeter wave frequencies. We expect that 6G will be able to use even more spectrum blocks. One potential spectrum block is between 7 to 20 gigahertz, like extending the current mid-band spectrum. Also, so-called terahertz frequencies will be utilized, that is referring to spectrum above 90 gigahertz. And then also even lower frequencies below 600 megahertz could be used for the extreme wide area connectivity, like IoT and some other low data rate connectivity. And of course, refarming from 5G eventually will be done to 6G technologies as well. And finally, I would like to note also here that if you look at some studies about the customer experience, this example is from UK market, and what is true there for all four mobile operators is that the customers who are using 5G tend to be more happy than those customers using only 4G technologies. And well, I don't know the exact background reason here, but I mean, our fundamental target here would be to make customers happy, and it looks like 5G is the technical solution which can make customers more happy, which is great. And also finally, here's one personal commercial break. So we have published a book about 5G technology with my colleague Antti Toskala and our friend Nakamura-san from NTT Docomo. So if you want to read more background here about the specification, performance optimization and devices, then I can provide the link to the book for you. So that is all from my point of view. I'd like to thank you for your attention today.
Thank you, Harry, for a wonderful presentation on 5G, 5G Advanced, and 6G. There are a few questions which we got, and let me show those questions to you if you like to answer them.
Yes.
So before that, Sunil sir, if you have any questions in mind.
You proceed, Ashok, then if it is not covered, then I will ask.
So there were three questions you can see on the screen. I'll read for you. The first one is that what are the research area the academic community may choose to focus with respect to communication technology of the future?
Good point. So in terms of research, I think I believe that there's still a lot of work to be done on the pure radio connectivity, using new spectrum blocks like terahertz frequencies, using even more advanced beamforming antennas, and also using more advanced hardware technologies to make this all happen. So kind of like using 5G technology, but even more. So even more antenna elements, even better beamforming, even more bandwidth. So clearly providing just better radio. And then also the other area of sensing is how to use the RF technology, not only for communication, but also this sensing part. And also potentially area is also the architecture. So how to kind of optimally design the radio network, not only from the air interface point of view, but also from the network architecture point of view. So maybe some examples.
Yeah. The second question, which is in the mid of the slide, is what are the features in 5G which are focused on rural coverage? Or maybe that question maybe for even 6G, if there is some focus for rural.
Yeah, so I think there's nothing like dramatic magic here. So spectrum clearly is one important topic. Another topic is antenna technologies. And the third one is all those kind of 3GPP evolution topics that we have now on table for release 18. So we need to combine all the RF antenna spectrum and the transmission solutions together.
Yeah. And the next question is do you think that adoption of Open RAN will lead to sharing of RAN active infra becoming very common or even mandatory in times ahead?
I think the Open RAN is not needed for sharing. So sharing can be done. Nokia has a number of customers globally using multi-operator core network, using multi-operator radio network, MOC and MORAN. And that clearly makes sense in some cases, like for example rural coverage. But I don't think Open RAN is not any mandatory requirement to make it happen. I mean, Open RAN of course has some other benefits in terms of maybe innovation flexibility, but it's not something which we need for the network sharing specifically.
Yeah, thank you. Sunil sir, if you have any question from your side.
On the last question about Harry, actually the point was that here there is a concept of passive infra being run by third parties and operators run on that passive infra. So whether this Open RAN will make the hardware part of the passive, that active infra, which can be given to all other operators to put their software in. Whether that kind of a model is thought of, or is it likely? That is what maybe the question is.
Yeah, I understand the question. I think that has maybe not been the main focus in O-RAN today. The focus has been more like this RU-DU flexibility. I think you are now referring to the case that we would have one common RU and then multiple DUs, which I think may be feasible, but also sounds fairly complex in practical deployment. Remember that the other area which you can do is MOCN, meaning that you are sharing the full radio access network, and then you have two different core networks, and that is feasible already in practice today.
Thanks. You mentioned that the 7 gigahertz to 20 gigahertz being the golden band, which can be put into use later for the access side. So now, as you know, there are a lot of point-to-point links, microwave links working like 15 gigahertz and 18 gigahertz systems working. So do you foresee that the countries will have to put some stoppage of further deployment of these links so that when 6G comes, the spectrum below the 20 gigahertz can be pulled and used for the access side? So do you foresee such kind of steps to be taken by the countries?
I know that there's a lot of challenges, so the idea was rather here to raise the discussion globally that these spectrums may be also valuable for the access technology in the wide area networks because of the improvements in the beamforming antennas, because of the improvements in RF. So, and I don't think there's any clear dedicated spectrum in that spectrum range today. So I think the industry has to work together for the WRC 23 and then 27 to try to make it happen. But I think there's no magic or simple solution here to how to proceed, sir.
There is one more question on chat box, sir. Can I read? Yeah. That is, can RF MEMS technology, MEMS technology is useful for 5G or 6G? If yes, what kind of devices we can realize using this technology for 5G and 6G?
What is MEMS technology? I'm not really familiar with that abbreviation.
This question is from Dr. Mahesh Angira. If you like to clarify, Dr. Mahesh, in the meantime, we can take another question. That question is from Ashok Kumar Jha, sir. Will the future broadband be mutually complementary? Means broadband and fiber will be supplemented by, say, 5G, FWA, or even by mobile signal of other operator?
I think complementary, yes, definitely. So I mean, the idea would be to use the best solution for the connectivity. In many cities, fiber connection is widely available, which of course makes sense. And then 5G should be focused on those use cases where the mobility will be needed. But then if you look at India and some other rural cases where the fiber is not available, in those cases 5G also may be the most efficient for the fixed wireless access. So I think it all depends on the case. So we need to just be able to pick the best technology for the specific use cases.
So on the previous question, Dr. Mahesh Angira had said this is RF MEMS is radio frequency micro electromechanical technology. I don't know. I have not heard of it.
Yeah, sounds like an interesting technology, but also goes beyond my understanding. So I can't really give any comments here. So indeed, I know that RF, of course, is an important area. So any kind of innovation is critical there. So.
Yeah. So I think there's no more question in the chat box. And sir, if you like to say a formal thanks to Hari Holma before we take the next session. Sunil sir.
Yes, Ashok. So it is always a great pleasure to listen to Dr. Hari because we have lived through mobile communication looking at the books edited or authored by Dr. Hari in the past few decades. So it is always very informative to listen to him. And he has taken time out for the session. As soon as we sent the invite, he was very happy to accept the invite and spare his time. So thanks a lot, Dr. Hari, and really look forward to interacting with you in future as well. Thanks a lot.
Okay, thank you, Sunil. Thank you for the audience.
Yeah, thank you, sir. Moving forward, our next section, section 3rd, is by Dr. Kiran Mukhavelli. He is Senior Director Engineering, Qualcomm Wireless Research. And the topic for him is the technology enablers for 6G. I think Kiran is already, I can see video. So welcome Kiran onto this webinar on 6G, the road ahead. And floor is yours. Over to you.
Thank you all. Thank you, Ashok and Sunil, for having me over. Let me start sharing my slides.
Yeah, please.
We need a quick feedback to make sure that things are coming out fine. Okay.
Yeah, we can see your screen, Kiran.
Okay.
Yeah. It's full screen visible.
Is it right?
Yes.
Okay. So looks like we're all good to go. Okay. Thank you again for having me over today. I'm Kiran Mukavili, a Senior Director of Engineering at Qualcomm Technologies based in San Diego. I lead the systems research here for our sub-7 GHz 5G advanced, and also looking at some of the new topics that are coming up for 6G. Today I'll be talking about the technology enablers for 6G. Before I get into this topic, I do want to use a quick slide to just point out the background about Qualcomm for any one of you that may not be aware of what we do. Qualcomm has been leading mobile innovation for over 30 years. We have been at the forefront of all the key milestones in mobile during this time, including starting with digitizing mobile communications, going from analog to digital. That was part of 2G. And then redefining computing, where we took connectivity and compute from desktop to smartphones as part of 3G and 4G. And now finally, as part of 5G, we're transforming industries where we're bringing all these technologies to various connected and adjacent industries, enabling the connected intelligent edge, where virtually everything is at the wireless edge. So this is where things stand right now, and this is an exciting time in terms of where 5G is right now, and as 5G is shaping up to give way to 5G advanced and 6G. And these are some of the topics that we'll look at today. So I do want to take a minute to point out the virtuous cycle that happens every 10 years or so. This is exactly what we went through for 3G, 4G, 5G, and it's instructive to take a look at this again in the context of 6G to see the different phases that we are likely to go through. It always starts off with a vision of what exactly we're trying to do for this new generation of technology, and what are the key problems that need to be solved. Starting with that, then we need to look at the invention phase, where once you identify the problem, what are the technologies that can help us solve these problems, followed by the proof of concept, where we build the initial prototypes to test out some of the new technologies that have not been part of the previous generations or not proven otherwise. Take them to standardization, where we also get buy-in from the rest of the ecosystem partners, have a common way of making sure that these new technologies work. Trials, where some of the early standards work, is then put to trial, put to test in OTA networks, in some real-world scenarios, and then finally go through the commercialization phase, where we're working with ecosystem partners, making sure the solutions can coexist and co-mingle with each other. And this is a cycle that's been happening every 10 years, almost on a predictable basis now. And we just went through this for 5G, and this is exactly the cycle that we are starting now as we speak for 6G. So I would say we are somewhere in the vision, invention, even proof of concept for some of the key building blocks that we'll see today as far as 6G is concerned, and then getting ready for the rest of the cycle to go through. So before we get into 6G, I do want to take a couple of slides to quickly point out what 5G has delivered, kind of baseline, the foundation that we have from 5G as launchpad. So 5G, that was the vision, and it has delivered on most of its vision and the promise, where 5G NR has turned out to be a unified, versatile, highly capable wireless platform, where we're able to provide diverse set of services, including enhanced mobile broadband, massive Internet of Things, mission-critical services, all using diverse spectrum, where we are able to deploy 5G in low bands, mid bands, 1 gigahertz to 7 gigahertz, and then high bands, which is the millimeter wave. And we have seen already some very interesting deployments in millimeter wave. And then diverse deployments, including private networks and public networks, apart from V2X and other kinds of networks that are also possible as part of 5G. And again, pushing the KPIs by an order of magnitude compared to what happened with 4G. So this is our launch pad, so to speak, and this is going to now set the baseline for what we can expect from 5G Advanced and then 6G. So with this baseline, again, 5G is not standing still, and Dr. Harry had already pointed out some of the things that are happening as part of 5G Advanced. I'll not go into too much of detail of what's happening with 5G Advanced, but it's definitely instructive again to take a quick look to see how some of those are going to help us evolve 5G Advanced and take 5G Advanced beyond into 6G. So this is a chart which lays out how 5G has brought in different features across releases. And I'm not going to go through all the features here, but I will want to point out how the evolution has been happening for 5G. So as we all know, release 15 was the first 3GPP release that brought in 5G, that set the technology foundation for 5G NR. And as part of this, EMBB, or the Enhanced Mobile Broadband Services, was introduced. And again, as we all know, so this is where sub-6 gigahertz with massive Mimo and enabling millimeter wave were two big innovations or key contributions as part of 5G NR. And this will also set the basis using flexible framework for slot configuration, scalable OFDM-based air interface, advanced channel coding. These are all the key building blocks of 5G, and then all the other features that are introduced later on build on top of this. So this was release 15, and then going into release 16, started expanding 5G to new use cases and industries. And in particular, if you look at features like positioning or industrial IoT, which got enabled using mission critical services and the EU RLFC 5G broadcast, integrated access and backhaul, and even private networks. So these are the new areas into which 5G started to expand using release 16. And then release 17 continued this process. We're just about finishing up release 17, where this expansion continues, and very exciting new features coming in. Again, so one of those is the reduced capability, the red cap, which starts to enable low complexity IoT. And it's not all the way there. It's a 20 megahertz. It enables a class of low complexity IoT. And then there's work in release 18 as well, where we talk about 5 megahertz. And that's again something that Harry had pointed out of how IoT is going to evolve within 5G. And then precise positioning, centimeter accuracy, and non-terrestrial networks. So a host of other features got added as part of release 17. And now, as part of release 18 and beyond, if you look at all the key features that are going to come through, and some of the exciting features here include full duplex Mimo, which is going to be a study item in release 18, and then hopefully will get defined as we look at later parts of release 18 and release 19. Extended reality, which is going to be a key building block for metaverse, smart repeaters, and again, a host of features. So as you can see, the point here is 5G is not standing still. There are a host of key features that are getting added on top of 5G. And again, given the flexible framework that has been the foundation for 5G, all of this becomes a natural progression for 5G evolution. So maybe I'll skip to this slide to point out the temporal view of 5G is how 5G is evolving. And this is important to understand because if you just take a step back, even for release 15, it's important to note that 5G actually built on top of LTE. So LTE was an essential part of the 5G platform. There was quite a bit of work done as part of LTE Advanced, which then got rolled into release 15, which could then just come in for 5G as a big release with large set of features, something that took LTE maybe 2 to 3 releases, and then all of those got rolled into 5G release 15. And that's something we expect to see again as we go from 5G advanced into 6G. So even in terms of the naming convention, the first 3 releases of 5G, which is 15, 16, 17, considered the foundational technologies of 5G. And then starting with release 18, it's going to be 5G advanced. And we do expect about 3 releases for 5G advanced before starting in release 20. We expect to see some of the study items for 6G show up, and in release 21 or so is where we start, or at least we expect to start seeing 6G getting defined as part of the specification. So that's the timeline we're looking at this point. So then it becomes instructive to see what are the topics that are already starting to get considered for longer term research for release 18, 19, 20 plus. And then some of these will probably get defined as part of 5G advanced and then become the foundation technologies for 6G. And some of those we just get studied as part of these 3 releases, but then will be left for 6G spec to come in and specify those. So again, just going through a quick list of some of the key areas that are getting some good attention. So it starts off with AI/ML data-driven design, full duplex, higher millimeter wave, enhanced positioning, terahertz bands, intelligent surfaces, green networks, RF sensing, new topologies. Again, I'm not going through the entire list yet, and I will go into details for some of these technologies, or at least point out some of the key research problems that start to show up as we look at some of these techniques and technologies and how to roll them into 5G advanced and 6G releases. So this background, let's start diving into some of the key research vectors which I think will enable the path forward as far as 6G is concerned. So as I said, AI/ML powered end-to-end communications is going to be a key building block. So this is where we're going to have data-driven communication and network design, joint training, model sharing, and distributed inference across networks and devices. There are going to be some interesting paradigms that evolve here, where the training happens and how the model sharing happens, and we'll spend a little bit of time just looking at some of the options and what we think will be a meaningful way to evolve this. Spectrum expansion sharing, there was a little bit of discussion. Harry talked about this, some of the new spectrum opportunities as well, and I'll also touch upon that. You see some exciting things showing up here, of course, including terahertz, which is always part of the 6G discussions, and it has a role to play, but then also for some of the lower bands as far as coverage is concerned. Then new radio designs, this is always going to be the core of any new generation of cellular technology in terms of what kind of coding, waveform modulation, apart from any other key innovations that can be brought to the table. Then merging of worlds, this is the metaverse that we are talking about. Some of this is already starting to happen as part of 5G advanced when we are bringing in XR, but then 6G will take this forward, and we'll see what kind of techniques are going to be possible to make this happen. And then from a network architecture point of view, so it's going to be the scalable network architecture with extreme disaggregation and virtualization at cloud, edge network, and use of advanced linear mesh topologies to address growing demand. And finally, communications resiliency in terms of both security as well as robustness to make sure that the networks are going to be tolerant to any failures and attacks. So with this, I will start diving into some of these topics in a little bit of detail. So let's start with spectrum. So again, for every generation, spectrum is going to be critical for the success of a particular generation. So with 5G, of course, we enabled mid-band and millimeter wave, and that has been the defining feature of 5G, when the 5G has also expanded to occupy the bands where 4G was deployed. We do expect to see some of similar paradigms extend over, but then also some new paradigms to show up. So license spectrum is definitely going to be the key. License spectrum is where we're going to have exclusive use of spectrum for a particular operator. That way they can offer their guarantees and quality of service and plan the network and everything. So that's still, of course, going to be there. That's always a starting point. And then also the unlicensed spectrum, 5G efficiently supports unlicensed spectrum, and some of that will also extend into 6G as well. But in addition to these two, we do expect to see some interesting models to evolve as far as shared spectrum is concerned, where if you look at how spectrum gets used now, of course, most of the spectrum is allocated, and I know that was also part of the discussion that came up around 7 gigahertz, 20 gigahertz. So, yes, it is all allocated, but then if you look at every geographical region at every point in time, is the spectrum utilization as efficient as it can be? Is it used at every point in time as well as space? And the answer is not necessarily. So can we do something better so that there's maybe a primary occupant that still gets its guarantee of service, but then we can also enable some secondary users that can come in and go away without taking anything away from the primary users. So that's always a starting point for shared spectrum. Can we do this in a more efficient manner for 6G? And we do believe that there will be some new models and some even influenced by AML where we can make this happen. So the shared spectrum is definitely, I think, one of the interesting things that will start to show up as part of 6G. And then just looking at some of the bands where 6G is going to happen. So yes, we will continue to have 6G deployments in sub-7 gigahertz, where we currently have 4G and 5G. And as part of this, one of the key design metrics for 6G will be to make sure that we're going to have efficient sharing techniques for smooth migration from 4G, 5G bands to 6G as far as sub-7 gigahertz is concerned. And similarly for millimeter wave, 28, 39, and 60 gigahertz, 5G is getting deployed right now, and 6G will come in and enhance some of the millimeter wave deployments and techniques that we currently have. So these two bands will see evolution and coexistence of 5G and 6G. But then there are also two other bands which are very exciting. So one is the new spectrum in the sub-terahertz and terahertz band. So this is where, of course, a lot of spectrum is going to be available, but the coverage will be an interesting challenge here. And of course, it's not going to be meant for deep coverage. This is going to be meant for short ranges, ultra high throughput. And this can also enable some very interesting use cases and functionalities, including advanced sensing, just given the kind of spectrum that we're dealing with here and the kind of bandwidth that we'll have in this particular band. This is going to be meant for what's also going to be interesting for this new spectrum is that this will also need some new foundational design to make sure that we are getting the best use of the band as well as the kind of bandwidth that we have in the spectrum. The other chunk of spectrum that's going to get very interesting is what we show here as FR3. So some of this is already starting to come under discussion even for 5G advanced right now, but we think the real potential of this will start to show up in the 6G timeline. So this is between the 7.125 gigahertz and the 24.25 gigahertz. So this is a spectrum where we think we will get the best of both FR1, which is the sub-7 gigahertz, in terms of the deep coverage that's possible. So this could be the coverage band as far as 6G is concerned for greenfield deployments. But it also gets the benefit of FR2, where we can enable wide bandwidths in the spectrum. So in some sense, it's going to be the best of both the worlds. So how do we make this happen? So how is this FR3 in 7 to 20 gigahertz or 24 gigahertz going to play out? So as an example, so if you just look at maybe 12 gigahertz or 14 gigahertz, which is roughly 4 times the carrier frequency that we have for 3.4 gigahertz, which means that the wavelength is 1/4, and for a given antenna panel size that we currently have for commercial solutions of mid-band deployments, 3.5 gigahertz deployments, we can pack in 16 times the elements. So, for example, we have commercial deployments with 192 elements. We have our OTA prototypes with 256 cross poles, 512 elements. So we have shown that we can have antenna arrays of this size even for 3.5 gigahertz. Now, keeping the same aperture, same antenna panel size, we can pack in 4 times the elements. So that, first of all, helps us to bridge the additional penetration or the propagation losses that we have in these new bands, just given the 4 times antenna elements and the additional beamforming gain that we get out of it. But it also has the benefits of FR1, where we can still do this using digital beamforming. We can go with our 64 TXRUs, 128 TXRUs, and we're looking at some of the low complexities ways of enabling this so that the complexity doesn't just go up as we start increasing the number of digital streams that we have. So as a result of all of this, what we see from our system level studies is that, first of all, the capacity can go up quite a bit because we can enable a lot more multi-user MIMO. So of the order of 2x to 2.5x compared to what's possible with 3.5 gigahertz, just because the beams are going to be much narrower and interference can be regulated. And we can pretty much match the coverage that we can get with sub-7 gigahertz deployments. So there are going to be very interesting research areas that will come up around this, including how do we enable hybrid beamforming architecture for the large number of antenna elements that we expect to see in these bands, coverage enhancements and beam management, power and energy efficiency or savings for base stations and devices. Again, given the larger number of RF chains that we expect to see in this batch. So this is definitely something to look out for as the discussions around 6G start to happen more and more. Second aspect is new foundational area interface. So whenever we have a new generation of cellular technologies, that's also an opportunity to bring in or to fold in the latest in terms of coding, modulation, waveform, and multiple access research. So, of course, with 5G, we have LDPC codes and POLAP codes that define the data channels and control channels respectively. And there are also advances with LDPC that are happening, and then there are also other classes of codes that are coming in. And we do expect some of this will start to show up as part of 6G standards as well. What's going to be interesting here is that as part of 6G KPIs, one of the expectation is always going to be that there is going to be an order of magnitude increase in terms of the data rates that we can support, capacity, complexity, power, efficiency, latency, and again, each one, whether it goes up or down in the right direction in a meaningful fashion. So it also becomes important then to make sure that we have the right channel code and modulation, for example, to support this extremely high throughputs that we're going to start talking about in an efficient fashion, something that can be implemented on a handheld form factor. So that's not going to change too much. If anything, the device is only going to get more and more compact with maybe wearables, smart glasses, smart watches, and other ways in which we'll start interacting with these devices. So this is going to be a very interesting challenge to see how we can support this high data rates. So again, quite a bit of work we expect to see show up around that. So some of the example research areas here are going to be energy efficient channel coding and modulation. Also, to be able to support different regimes of operation. So 5G already, for example, is able to go up to 10 Gbps and beyond, and then start talking about 50, 100 Gbps kind of data rates. We'll still have applications that sit in different regimes of this, and then we want to make sure that we stay optimized for each one of these regimes. So it's going to be, I think, a collection of techniques that will get employed to make sure we complete the entire range that we'll need to have. And then waveform for high PA efficiency and high spectrum efficiency, multiple access schemes to support high cell capacity and massive connectivity. Again, as IoT explodes, expect to see more and more devices to stay connected on the network, and how do we support all of this efficiently. It's going to be another key research area that's going to show up. AI/ML powered end-to-end communications, something I touched upon, and I'll have a couple of slides on this to give you a vision about what we see coming up here. So the key here is AI-powered end-to-end communications, because it's possible, and even today we do have ML-based enhancements that either reside on the device or in the network. They don't necessarily have to communicate with each other and can be transferred to the other node. If the device has an algorithm which is enhanced by some ML aspects, it stays within the device and it's just implementation specific and nothing to do really with what's happening with the standards or on the network side. So what we're talking about here is an end-to-end optimization where we're able to customize the entire wireless system and the configuration to a given wireless environment. As the wireless environment changes, you want to be able to customize and update. So it's going to be a data-driven approach, end-to-end approach. And part of this is going to be joint training between the nodes, model sharing, and distributed inference across networks and devices. So each component of the ML sitting at a particular node is going to be aware of what's happening at some other component within the entire network. So this is where we want to be able to leverage the intelligence that's going to reside now with the edge devices, including the user devices, the disaggregated network, and then even the distributed cloud, which could be, again, edge cloud and central cloud. So the intelligence is going to be distributed, and training and inference is also going to stay distributed as we evolve to this model. So some of the example research areas here would be spectrum intelligence, for example. That's one of the things I pointed out earlier as well. Shared spectrum, how do we enable that? And with some of the ML techniques, we can actually start better sensing of how spectrum gets used and put that to better use. And then similarly, network and system intelligence, where we can actually have ML-driven network resource management and also network energy savings to drive better efficiency. And then transmission intelligence and adaptive based process. This is closer now to the physical layer, where we can start our channel state feedback designs based on ML. So these days, the baseline with 5G and 5G Advanced is either TDD reciprocity, where we sound the channel and then make use of the reciprocity on uplink and downlink, or explicit channel feedback, where the device actually figures out what the pre-coding should be and lets the network know about it. But then these are only some features of the channel that are being captured as part of this feedback. So we are, again, some of this is starting to show up even in release 18 as part of study, and then will start to get defined even as part of 5G Advanced. But can we actually have ML models that extract the key features of interest and then share between themselves on the device and on the network, and then use that for not just communications, but even the other functionalities that we start to talk about? Similarly, beam management, sensor fusion, and a lot of these other functionalities that start to show. So, related to the end-to-end ML, one interesting question that comes up is, how do we do the training and inference and model management? So clearly there are going to be three options that show up here. Is it only on the G node B, where the device can collect all the data and measurements and keep feeding the G node B, the G node B then trains its ML models based on all the data, and then all the inference and intelligence resides at the G node B. The device is just feeding all the training data. So this is one way to implement this, and this is not necessarily exploiting any of the intelligence that can reside in the device. One other model could be where all the intelligence is at the device only, where the network is actually helping the device. In some cases, it could even provide assistance or configure the ML model, but then also provide all the training data, train the ML model on the device, and then all the inferences happening on the device. So this is another extreme where we may not then be putting to use some of the intelligence that could be at the network, and network could actually have some powerful GPU sitting there as well, which is going to be beyond what the device can carry. The third option, which we think is going to be the most interesting one here, is what we call the cross-node ML, where both the device and the network are coming together. So there's going to be joint training and joint inference between the two, where auto-encoder networks, for example, is one instance where you could have an auto-encoder on one side and auto-decoder on the other side, and then it's the two ML networks that are then exchanging information, extracting features as needed, whether it's a channel or any other aspect of communication that we want to enhance using ML, and it is left to that this particular implementation. So this is the way we see things go forward, and again, release 18 study item that's happening right now, I think is going to be quite instructional in terms of seeing how the framework for this can be laid out. I hope I'm doing okay on time.
Yes.
So in terms of duplexing schemes, again, yet another exciting field, and where we think quite a bit of innovation is possible. So traditionally, we have had our FDD or TDD techniques, or even dynamic TDD, frequency diffusion duplex or time diffusion duplex. And dynamic TDD has always been in spec, but one of the key challenges here has been how do we manage the interference? If you change the direction of uplink or downlink in one portion of the network, what do we do with adjacent cells, and how do we manage this interference? And there is some signaling provided in 3EBP to at least go measure, but then managing this in real deployments has been a challenge. So what's getting exciting here is, of course, we've talked about full duplex for a while in academia, as well as there have been some prototypes showing that full duplex can be made to work, but all of this has been, I would say, in a limited setting with smaller transmit powers, 20, 23, 18 dBm Wi-Fi kind of settings, which is really not going to move the needle as much as far as cellular deployments are concerned, where we need to be able to enable these techniques for macro networks operating at, as far as 5G is concerned, even at 75 dBm, 80 dBm kind of ARPs, and massive MIMO kind of architectures. How do we make that possible? So this is where subband full duplex, which is what's shown here, gets quite exciting, and we have prototypes right now which show that we can actually make this work in high power macro networks. So in terms of specification, it's starting to show up. So for example, release 17 supports full duplex and subband full duplex for integrated access and backhaul, and release 18 is currently expected to support, at least starting off as a study item in release 18, and then beyond release 18, we'll start seeing specifications for this. But this is just the starting point. We expect 6G to take this further and even enable flexible duplexing for expanded number of scenarios, and also different device form factors as well. And that's always going to be one of the challenges within the 5G region. So as part of the research here, so some of the example research areas would be, first of all, how do we get our antenna RF digital self-interference cancellation? And I'll go into this in a little bit of detail in the next slide to point out the kind of challenges you'll run into as you start looking at massive MIMO kind of deployments, which is also the second bullet here: complexity reduction for massive MIMO, cross-link interference mitigation, and network coordination. If we are going to now have up and down configurations which are not exactly aligned between the neighboring cells, and then adaptation between different modes, whether you go in a sub-band full duplex mode, or TDD mode, and then managing SU and MU MIMO in this configuration. So let's take a quick look at the key enablers for full duplex air interface. So the important thing here is to make sure that we are able to enable this in a macro network, where if you take 5G as an example, 5G deployments, we could have a macro network with 64 TX 64 digital chains. So if you have transmission from all of this and reception from all of this, so there is self-interference now, and you have to start cancelling this or 64 times 64 kind of combination of chains. And that's going to be one of the challenges. How do we make this happen? Is this even feasible? And how much of the cancellation can be achieved? So we already have prototypes now that show that you can actually do this in an intelligent fashion and get most of the residual interference cancelled out. But again, the starting point for a full duplex at any point is going to be to try to get as much isolation as we can get. Try to solve the problem before it happens, which is, the dimensions that we have would be the spatial dimension, frequency, and the beam direction, which is also some form of spatial direction. So from a spatial isolation point of view, so if it's a device, then typically we talk about a duplexer where your TX and RX can be isolated. If you're looking at G0B kind of an implementation, so for spatial isolation, so one of the techniques we are looking into right now is to take the entire array that we have and can we divide this into subpanels and have separation between those subpanels so that we start off with a good chunk of isolation right there in terms of the 80 to 90 dB kind of isolation numbers that we are looking at here. So again, it does look simple enough that you can actually just have a different portion of the array for TX and RX and just get the isolation. But no, it's not going to be as simple. If you are targeting 80, 90 dB kind of isolation, you have to bring in some special techniques in terms of how the arrays are even constructed. Again, so in the MWC22 that's coming up, we'll show some of our prototypes and demos where you're able to get to this kind of isolation numbers. And that's the starting point. But we have to build in a lot more isolation to be able to make this functional, just given that our downlink transmit powers are starting off at about 75 dBm and our uplink reception powers going to be around minus 90, minus 95 dBm. So we're talking about a huge delta in transmission and reception power levels, and how do we bridge that gap? So we have to build it up step by step. So spatial isolation and then the frequency isolation, and this is where the subband full duplex comes into picture, where instead of allowing uplink and downlink as would happen in full duplex. So what we're saying here is let's take a chunk of the spectrum and allow that for uplink instead of allowing uplink to collide completely with downlink all across the spectrum. And this by itself will also give us another 45 dB of isolation between downlink and uplink, and then beam isolation and so on and so forth. So again, just wanted to point out some of the things that are going on right now, even as part of 5G Advanced to build this up, but then some of these things may start to mature as we start getting into 6G. Again, a lot of interesting research problems here for academia and industry to start looking into, and just one other example here. And then reconfigurable intelligent surfaces, yet another exciting technology that's showing up. The goal here is to have these large panels with individual elements that can be controlled, where the control is for the phase of the reflected array or the reflected beam, or in some of the more advanced implementations, you can even start manipulating polarization and other aspects of RF that come in. So as a result of this, what happens is you can have an incident beam and then you can control where the reflected beam goes. And the goal is to do all of this in a low cost, low power kind of an implementation. So that's where you could have these large panels, which could even go on the sides of buildings, and then use these to be able to reach some of the locations in the network which probably cannot be covered otherwise. So this is an example here where there's a wall and you're trying to go through the wall. So put an intelligent, and again, a simple cartoon just to explain what we mean by plugging in the coverage holes here. So trying to go around the wall in this particular case. From our simulations again, we have seen that we can get quite a bit of network capacity improvement by putting in nodes like this, and a lot now depends on how much of this can be realized and practiced using technology. So how well this will take off will depend on how well we're able to do on the C-swap, which is the cost, size, weight, and the power consumption of this. So the main selling point here is that these are all passive elements that are going to be controlled with very low power control that's sitting to adjust the characteristics of these passive elements. So how well can we do this and how large these arrays can get is going to be the key here. So again, very exciting field. A lot of papers are also coming out of academia, but the important thing here will be to see if we can actually build this out and if this can be made to work. So some of the example research areas here include research into materials and metasurface design with wide bandwidth and high-speed configuration and reconfiguration, cascaded channel model, because now you're looking at the channel model that goes from the G node B to the UE through the intelligence surface. So can we get access to each one of the individual components of the channel, or do we always have to look at the cascaded channel, and how do we do a system design based on that? How do we do a link adaptation based on that? Can we support Mimo using this, or is it always a single layer, single link that can go through this? So there's a lot of interesting questions that can be posed and waiting for answers here. Yet another one is the joint communications and sensing. This is the sixth sense that Harry had mentioned in his talk as well. So the goal here is to see how we can integrate some of the non-communication aspects into communication systems. So with 5G and 5G Advanced, and even with some of the earlier cellular systems, we already have a notion of this where positioning is part of our communication network. We allocate some resources for positioning and doing some of the non-communications aspects. But the goal here is to take this further into even sensing, where so with sensing, so what we're trying to get to here is even make the cellular deployment a radar system where we're able to completely map out using our RF signals what's happening in the environment, and then use this whether to enrich user experiences as we move towards metaverse, or even to optimize some of even the communication aspects. Once we know where or how the 3D world around us looks like, where the reflectors are, which direction to avoid and which direction to go in. So again, a host of new functionalities and features that can be enabled if you can get this in. And some of the example research areas here include waveform design for joint communication sensing, resource allocation and feedback design, optimizing communication link based on sensing information that's derived. Again, just a tip of the iceberg here, but very exciting field that's showing up here, and I think it's going to play a very important role in how 6G gets defined. And then expanding the role of millimeter wave. So 5G has established millimeter wave communications. It's already getting deployed, getting commercialized in many places, and it's only expanding with every quarter and with every operator that's getting added to this. But the research and evolution of this will continue. So, of course, there's always more that can be done. There's always more that can be done with improving coverage and robustness, device size and power, beam management, topology enhancement. So these are all ongoing research areas, and this will continue to happen in 5G Advanced and even going into 6G. So some of the example research areas here include power efficient RF front-end and beamforming architectures, waveform and modulation for better power efficiency. So this goes back to the earlier point that I mentioned, that with 6G there's always an opportunity to bring in new air interface and new aspects of waveform and modulation, and millimeter wave is yet another place where we can continue to look at 5G and 5G Advanced have done this in a particular manner. Can we push this further, or is there also another fundamentally different approach that we could also take to the overall millimeter wave design? Then beam management enhancements, topology enhancements, as I said. So again, a host of interesting research areas that start to show up even as we continue to expand the role of millimeter wave. And then network energy efficiency and green networks. So again, with each passing day, there is more and more stress on how to make our cellular systems more energy efficient. So 5G started some good work in this field, where one of the key differences for 5G compared to even 4G is that we took away always-on symbols. So there's no always-on pilot, and that's a starting point. Already it was shown that just taking away always-on pilots can save so much of power in the middle of the night when there is no user. It can actually shut down the entire G0P and then change the configuration so that the periodicity goes down significantly, leading to substantial power savings and energy savings. So that's a starting point, and beyond that, of course, we have narrow beam direct transmissions to make sure all the energy is getting used efficiently. And now, even in release 18, there is a specific work item that's been defined to enable green networks and network energy savings. So this is something that's going on in 5G, but this is just the beginning. There's going to be more and more stress and focus on making this happen even as we get into 6G. So some of the example research areas here would be network energy saving techniques for Mimo, mobility, power amplifier efficiency on the network side, distributed topology, and then trade-offs between network energy saving and performance. Because we could always try to save energy on the network side, but then we need to make sure that it's not coming in at the expense of any user experience or even shifting the burden onto the UE. And any technique that you start looking into will always come with one of these caveats that you are actually taking away some of the KPIs. So that's going to be the interesting challenge here as far as the network energy efficiency is concerned. So again, I went over several topics here at a somewhat high level just to point out how we see 6G shaping up and what we think will be the key building blocks, and also some of the research areas that are involved in each one of these key building blocks. And as we put all of this together, this is where we start seeing the 6G experiences, the new human interface in terms of merging of the worlds, metaverse coming together, where with metaverse, essentially what's going to happen is we start off with a physical world, start digitizing this using ubiquitous low power sensing and monitoring near real-time action. So we have a complete representation of a physical world in a digital world, and then use the virtual world to start manipulating the digitized real world. And this is exactly what gives us this immersive interactions to take human augmentation to the next level. So this is our vision about how all the three worlds will come together and provide this new user experience in terms of metaverse, which is the goal. And in some sense, 5G has already started to enable this, and 6G is going to take this to the next level. So with this, I think it's a good time for me to conclude. But as part of conclusion, I do want to point out that even as we look at all the potential for research areas for 6G and how it's going to evolve, the baseline or the foundation is going to be 5G. So as I said, 5G is not staying still. So 5G is evolving. So we have 5G Advanced now, which is bringing in many of the features that we talked about even as part of 6G. So some of this will start to show up as part of 5G Advanced, and some of this will get studied and will get ready in time for 6G. But whenever 6G comes in, and we do expect that it's going to be around the release 21 time frame, but it's really the evolution of 5G and 5G Advanced that's going to set the stage for 6G to come about. That's going to be my last slide. Thank you. Thank you all for your time and attention.
Yeah, thank you, Kiran, for I think for wonderful presentation. I think some mic is open. Just a moment, please. Yeah. So I don't know why Holly is coming. So I read out some questions taken from the chat box for you. Just give me a moment. I'll just.
Sure. I can stop sharing if you need to share.
Yeah. Please. Yes.
Okay, so it looks like you're already sharing.
Yeah. So the one question is from academia. What are the research aspects to be addressed by the academia in mobility performance studies with 6G integration? How do you visualize it as different from 5G integrated one? Is it only in terms of enhancing data transfer rates?
No, so actually, I touch upon one of those areas here, and so definitely mobility performance and new paradigms for mobility is going to be a key research area going into 6G. So, for example, there are notions of cell-free Mimo, and we talked a little bit about this even at the beginning of 5G, where we call it uplink-based mobility, where you don't necessarily have to have a fixed notion of a cell and the user moving from cell to cell. Can the cell actually follow as the user is moving, so that the user doesn't have to do as many measurements and then worry about handoffs? And because right now, even for mobility, so we have done things where it's 0 millisecond handoff or tabs, dual access protocol, and things like that, where we're trying to minimize any impact on user experience as part of mobility and handoffs. But this can be taken further, and the eventual goal would be to remove any notion of a cell from a user experience point of view, so that it's completely glitch free, any kind of mobility. So yes, there's going to be a lot of attention around this topic for sure.
Yeah, next two questions are about cell-free architecture in 5G advanced and 6G. Another is that what shall be key role of AI ML in 5G or 6G applications? If you like to touch upon these.
Yeah, sure. Again, there were a few more slides and some more material around cell-free that you wouldn't have time to get into. So I talk about those, but it again goes back to the first question that was brought up. So both in terms of mobility as well as start talking about distributed massive MIMO. So 5G has enabled massive MIMO, but can we now take these TRPs, start putting them apart? So we do have comp as part of 5G, but it's to a limited scale. We envision this to start taking shape in a much wider form, and that's where the so-called cell-free architectures will start coming in as well, both from trying to simplify some of the baseband processing, because once you start increasing the number of nodes and TRPs that you have out there in the deployment, it's likely that you probably don't even have to go to some of the optimized pre-coding techniques that we have right now, which are going to be complex as you start increasing the number of nodes. Just given the increased dimensionality that we have, maybe some of the simplest schemes like just match filtering with the increased number of TRPs and antenna arrays that you have will actually start doing the role. And then we can start enabling some distributed scheduling and all the other related aspects of comp. So yes, it's going to play a big role as well. You're the key research area, everything.
Yeah.
And then the third question: what developments are being done in AML for end-to-end communication?
I think you covered it. I think you covered it while you presented it.
Yeah, so that's upon a couple of things. I didn't go into the specific problems that we're working on, just because I wanted to give some research directions here at a high level. But then there are also some very specific problems that I can also point out, and maybe just to mention here, channel state feedback is one aspect where we see some concrete problems, and then even non-linear PA optimizations, waveform designs, positioning enhancements, beam management. So these are all concrete problems where you're already starting to see that AML can actually start to improve performance.
Yeah. Your voice is not coming. Are you?
Oh.
Yeah. Now it's coming. I think.
Oh, is that right? Okay.
In between, it was not there. So can I take next question? There are many questions coming in the chat box. Let me take this one. This question is about your slide on full duplex air interface. He's asking that I'm curious to know the status of the silicon development, if you can add more detail on whether the solution include baseband or switching between transmit and receive happens at the analog level. What distance you were able to achieve if solution got tested?
Yeah, sure. Yeah. So again, the solutions and the techniques that I pointed out, so you still continue to have your transmit chain and receive chain, and the goal here is to make sure that there is enough isolation built in between the TX and RX chains, and that's where all these different domains come into picture: spatial isolation, frequency domain, and the rest of it through inference cancellation. In terms of the range, so what we're talking about here with macro networks is we want to be able to match the coverage that we have otherwise with TDD. If anything, we want to use full duplex to improve the coverage of uplink, because now we get more opportunities, because in TDD, typically these are all downlink centric. So you could have maybe 3 slots for downlink, 1 slot for uplink, or 5 slots and 1 slot. So just given that the data is mostly downlink centric, most of the configurations are also downlink centric, which means that first of all, the uplink coverage is going to be somewhat limited, because you're starting off with a UE which does not have as much power as the G node B. It also gets fewer opportunities to transmit. So as a combination, the uplink gets challenging. So with full duplex kind of, or sub-band full duplex kind of techniques, what we are doing here is providing more opportunities for uplink. So you could always have an uplink that's going on, which means that the UE can transmit more often, helping with both the coverage as well as latency. And in terms of the range question that was asked here, the goal is to make sure you're able to match the range that we have otherwise with TDD, or even improve the range for coverage for uplink. So the demo that we're going to show is for a macro cell which is able to go out to even a kilometer kind of a range.
Yeah. So there are many questions pouring in. So I don't know how much time you may be having. I'll just read these 3 questions. You answer whichever you want to answer in a sequence. So 64 elements may not be enough for good gain in sub 7 gigahertz band. I think they're talking about Mimo, massive Mimo. Do you think extreme Mimo is economically feasible for CSPs, that is telecom service providers? The similar question for will there be any metamaterial based antenna, which your slide talked about? And what kind of a new modulation scheme may be considered for 6G? These are 3 questions.
Sure, yeah. So maybe for the first one, 64 elements. Okay, to start with, just to set a number out, so most of the commercial deployments these days have anywhere between 128 to 192 elements for the macro deployments as far as the massive MIMO is concerned. And we have our OTA prototype in our campus with 512 elements, 256 crossbows. So in terms of where things stand right now, we are definitely beyond 64 elements. But at the same time, massive MIMO panels and architectures come in all sizes and shapes. Not every deployment may need a panel which is as large and with 64 TXRUs and 192 elements or 256 elements. You may have some deployments with smaller cells where maybe just 64 elements and 32 TXRUs or 16 TXRUs may be good enough. So in that sense, so it depends on your cell planning and what kind of coverage and capacity you're looking for that particular cell. And then as we go forward, as we start looking at these new bands, we do expect that we'll be able to scale this up to even 2K elements. And from a feasibility point of view, we think it is feasible. Complexity is going to be one aspect, but then that's where some of the advances in even the baseband processing as well as algorithm optimization is going to help out. Metamaterial based antennas in 5G advanced. So as I said, the 5G advanced and 6G, there's going to be some blurring of lines where things start to show up. As the technology gets ready, it'll start finding a role for deployment, a place for deployment, and some of the technologies that we have right now will start getting replaced. But whether it's going to be for massive MIMO networks or more in the context of reconfigurable intelligent surface, it's likely that it'll first show up in a smaller way for this kind of nodes, and then become part of massive MIMO. And then new modulation schemes apart from OTIM. So OTIM, again, I would say it's maybe more of a waveform in terms of modulation schemes. Because right now we have a form kind of modulation schemes. So there are, again, some very specific scenarios and use cases where even ML-based modulation schemes that we have looked into, which can help in certain scenarios. And that's where I think 6G is going to be an interesting collection of solutions depending on which regime you're operating in and which particular use case you're going to target. So it's going to be optimized for each one of these scenarios. So we'll see how the solution comes apart. But yes, again, whether you can give a name to this new modulation schemes, if it's ML inspired, it's always going to be tricky. It may not be as regular or as pleasing to the eye as they're used to with some of these other core modulation. And that's just an example.
Yeah, so thank you, Kiran, for wonderful presentation on covering all aspects of 5G, 5G advanced, 6G, all research area. And you have answered so many questions, and there are, questions pouring in. So maybe if I send these questions to you, and if you want to give answer, you can email us, and accordingly we can answer these guys, because it's already 7:30 here, and so I now request Sunil sir for any final conclusion and vote of thanks of this particular event. Sir, over to you.
Yeah, sure. So it has been an exhaustive presentation from Dr. Kiran, and that too very early morning, before 4:30 in Santiago. So no words can express my thanks and gratitude for coming and telling us so exhaustively about the latest cutting edge areas in technology. So, and that too, Dr. Kiran has highlighted the research areas in almost every slide. He has highlighted the potential research areas, so that all the youngsters and faculties listening in from academia in this webinar, I'm sure they would have been benefited with the tips that he has shared. And Qualcomm being the innovator and the technology company that it is, and his Dr. Kiran's presentation has really reflected that depth that he has and his company has. So I'm really thankful to Dr. Kiran for the extensive presentation and patiently answering to numerous questions. I also thank Jitendra Singh of Qualcomm India to facilitate Dr. Kiran for this session, which was very useful and which was a very apt third session for the webinar to conclude. And he has really taken us to the 6G. Maybe 10 years down the line, we'll be seeing a digital avatar of Dr. Kiran coming out and sitting along with us in the metaverse and conversing with us. Really, after 10 years, we'll see that. So thanks a lot, Dr. Kiran, for sparing this time.
Thank you for the opportunity. Thank
Yeah.
you for the opportunity to share our views.
Thank you, sir. Thank you, Kiran. And with permission of chair right now, Srivastava sir, can we end the session, sir?
Yes. Thank you very much, Dr. Kiran. Wonderful presentation.
Thank you, sir.
Thank you
sir.
very much.
Thank you, sir. And thank you all the participants for joining. Thanks a lot. We'll send you the PPTs or recorded material to you over the email, or we'll put up on our website and give you the link. Thanks a lot. Thank you, everyone.